Well, hello once again, ladies and gentlemen. Mr. Dorfler here for your daily dose of Dorfler. One of the last daily doses of Dorfler for this week. So we are here in Chapter 5, Section 2 on the last part 3, looking at energy. So far, we've talked about kinetic energy. We've looked at work kinetic energy theorem. And today we're going to be talking about potential energy. There are really two types of potential energy that we are going to look at today. But you're going to have three formulas that you're going to want to write down. Okay, so let's talk about what potential energy is. Okay, it's the energy associated with an object simply because of the position, shape, or condition of the object itself. If we think about a wrecking ball, I know it's kind of an old one, doesn't really exist anymore in as much as it seems to have existed. But as you take that big wrecking ball and lift it up higher and higher from what we call a 0 point, or a point in which we compare the distance between the object and the point in context, then we can determine what potential energy it has in that case because of its position. Okay, we also have gravitational potential energy. It's the potential energy stored in the gravitational fields of interacting bodies. Gravitational potential energy depends on the height from a 0 level. Okay, so here's your first formula. Gravitational potential energy, PEG. You might even see it written as GPE, depends on what book you look at. Is equal to the mass times gravitational potential energy, gravitational acceleration times the height of what the object is from the 0 level that you're measuring. We also have what's called elastic potential energy. It's the energy available for use when a deformed elastic object returns to its original configuration. So whether we take like a slinky and stretch it or compress it, it's going to have elastic potential energy. And its formula is PE elastic is equal to 1/2 kx squared, where k is actually the spring constant and x is the distance either compressed or stretched. Now, the spring constant, it's a parameter that measures the spring's resistance to being compressed or stretched. Now, it's kind of like a way of categorizing springs, okay? Different springs have different uses. The spring in a little clicky pen, okay? There's a spring inside of here. It's very small, very thin. It's it's kind of developed and calculated for use in this device. If you look at cars, their suspension system oftentimes uses really thick, heavy-duty springs, okay? It's got a different task than the spring in here. So it's going to have a different spring constant. Now, in your solving of problems in the couple practice exercises we're going to do, as well as the problem bank we're going to do. Speaking of problem bank, again, I'm kind of tossing these randomly here. Your problem bank, which one is this? D? Yes. You are to do the following numbers, okay? You are to do number 1, number 5, number 6, 7, 9, and 10. Again, these are the questions that you are supposed to do. 1, 5, 6, 7, 9, 10. So there you have it. Anyway, you're going to experience questions where you solve for gravitational potential energy, where you solve for the elastic potential energy. And one we're getting ready to do now is where we have to solve it for total potential energy. So that is where we have to determine and calculate both the elastic and gravitational potential energies of the scenario and sum them up to determine the total potential energy in a given situation. So let's look at this. We have a 70-kilogram stuntman who is attached to a bungee cord with an unstretched length of 15.0 meters. He jumps off a bridge spanning a river from a height of 50.0 meters. When he finally stops, the cord has stretched a length of 44.0 meters. Treat the stuntman as a point mass, basically meaning that is the only mass that we're going to worry about. And disregard the weight of the bungee cord. Assuming the spring constant of the bungee cord is 71.8 Newton per meter, which is the unit for the spring constants, what is the total potential energy relative to the water when the man stops falling? Okay, so we have a ton of information here, but one thing that's not quite jumping out at us is that, when we're talking about gravitational potential energy, we have to determine what a zero level is. Well, in this case, it says it right here at the very end. The total potential energy relative to the water. So it says that he jumps off a bridge spanning a river from a height of 50 meters. So that bridge is going to be 50 meters above the surface of the water. So that means that the zero level is going to be the water. And so we have to document what distances, what lengths we have, everything that we have, just so we can make sense of it, because there's so much going on here. Okay, so we know the mass. Again, the mass is the mass of the stuntman, 70 kilograms. The spring constant, the K, 71.8 Newton per meter. Gravitational is going to be constant here on Earth, at least at 9.81 meters per second squared. Now, our height, okay, we have to use our height when we are calculating the gravitational potential energy, okay? And the stuntman started at 50 meters, and it said that the elastic bungee cord stretched all the way to 44 meters, okay? So in order to determine how far that stuntman is from the very bottom of that bungee cord to the water, we have to take the total height of the bridge from the surface of the water and subtract from that the overall length that the bungee cord stretched, which was 44 meters. And we find out that the stuntman stopped his fall at 6 meters above the surface of the water, our zero level. Okay, so H is going to be 6 meters. Now, since we're trying to find our total potential energy in the situation, and we're involving both gravitational and elastic because of the bungee cord, excuse me, we have to determine, figure out how far did the bungee cord stretch. It said that it stretched to a length of 44 meters, but it also had an unstretched length of 15 meters. So again, we have to take the difference and find that the length of the bungee cord stretching was actually 29 meters. Okay, so we need to figure out what the total potential energy is. Take a deep breath, okay, and think of these as individual calculations. Okay. To find the total potential energy, we take the gravitational potential energy and the elastic potential energy. We sum them up. But let's solve for each one of these components individually, okay? Gravitational potential energy is mass times gravity times height. Elastic is 1/2 kx squared, okay? Now, I said that there are 3 formulas to this. You want to go ahead and add this total potential energy formula here as well, okay? Just so you can have it. So let's solve these on their own, okay? So gravitational potential energy, we take its mass of 70 kilograms, multiplied by gravity at 9.8 meters per second squared, and multiplied by the height that the stuntman is in comparison to the surface of the water, which is our zero level. We find that its gravitational potential energy is 4.1 times 10 to the third joules. The elastic potential energy from the bungee cord, take 1/2 times K, the constant of 71.8 newtons per meter, multiply it by the distance that it was stretched at 29 meters and square it, and we find that we have 3.02 times 10 to the fourth joules. Well, once we determine the amount of energy, potential energy for each one of these situations, and to find the total, we sum them up, and we find that we get 3.43 times 10 to the fourth joules of total potential energy. Okay? So, that problem is one where it involves both types that we don't see every time, but we could see. Now I'm going to go and do some practice ones where from your book. So once I get this situated, I want you to open up your books to page 172 under practice D. Okay, 172 under practice D. Let's look at number 1. Okay, number 1 says a spring with a force constant of 5.2 newtons per meter has a relaxed length of 2.45 meters. When a mass is attached to the end of the spring and allowed to come to rest, the vertical length of the spring is 3.57 meters. Calculate the elastic potential energy stored in that spring. Okay, so what we know is our constant is 5.2 newtons per meter, and we know that we have a length that is stretched for this spring, which is we have a 3.57 meter length when it is stretched, minus what it starts out when it's just relaxed at 2.45 meters. We find that we have an actual stretched length of 1.12 meters. So, using the formula for elastic potential energy, we have 1/2 kx squared. And so we plug in our numbers here. K is again 5.2 newtons per meter. Our x was 1.12 meters squared. Plug that in your calculators, you can get 3.3 joules. Okay, that was number 1. Next, we're going to skip to number 3. We're only going to do 3A. Okay, 3A. It says a 40-kilogram child is in a swing that is attached to ropes that are 2.00 meters long. Find the gravitational potential energy associated with the child relative to the child's lowest position under the following conditions. So when the ropes are horizontal. Okay, so if we were to draw a picture, okay, here is a little stand for the swing, and here is the child who apparently isn't being watched by anybody because they are perfectly horizontal to the ground. Okay? I'm sure we've all tried to do that at some point. Anyway, we are asked to calculate gravitational potential energy. So, let's take a look. We know that the mass of the child is 40.0 kilograms. Okay? We know that the height will be 2 meters because these ropes are 2 meters. When it's vertical, it's going to be 2 meters from the ground. Or sorry, when it's horizontal, it'll be 2 meters from the ground. So, the other thing we know is our G, 9.81 meters per second squared. So, to solve for gravitational potential energy, mgh, so our mass of 40.0 kilograms times 9.81 meters per second squared times 2.00 meters. We plug that into our calculator and we get 785 joules. Okay? So, you're going to see problems like that in your homework. So again, review the problem questions that I said to do for your problem bank. Circle them on the problem bank paper that I'm going to post separate from this video. Okay, so again, if you have any questions, let me know. Send me a message or anything like that, and I can hopefully clarify anything you might need. So have a good day. Don't forget you have a quiz at the end of the week over sections 1 and 2. Make sure your formula sheet is up to date. I'd be reviewing any practice ones that we have done. But yeah, we will see you later.